Okay, good. So we are set. Let's start with taking questions. Yeah, the urgent questions from yesterday. Okay. Oh, there is some issue that one of you, Tuni, cannot hear. But
no,
okay,
I think now probably now
yeah.
I think should be okay.
Yes, now I hear.
Okay, good. So there is a question from Tista. The question is that if we have two holes and we draw two different closed curves around the same hole in two different ways, starting from the same base point, which are not homotopic, but have the same winding number, the presence of the second hole makes the two curves non-homomorphic in this case. Then it will cause a problem then will it cause a problem when we are trying to classify homotopy equivalent loops of winding using winding numbers only? No, because you would find that this is one of the exercises that we did. Let me just open a black white sheet. Yeah. So you're thinking about case where I have two holes, okay, 1 and 2, and I choose a base point I, okay. I think about this, okay, and I think about this, okay. So irrespective of the second hole, the one has a winding number of 1 and the other has a winding number of -1, okay, around the hole, right? So they are distinct because they belong to the different classes, right? So what is so in the first case, the n clockwise is 1 and n anti-clockwise. Sorry, n clockwise. So n clockwise is 1 and n anti-clockwise is 0. So for this case, okay. So then n is equal to 1. Okay, well, I mean in one convention. In the other case, similarly, n clockwise is equal to 0 and n anti-clockwise is equal to 1. So n is equal to -1. Okay. So these have different winding numbers. Okay, a +1 and a -1 are different from each other. So they should not be. They cannot be deformed into each other. Okay, so in presence of the hole, I mean irrespective of the presence of the second hole. Okay, so but what I was saying is that the difference would remain conserved even for the first, even for one hole case. Okay, for the two hole case, what the extra feature that you would add is that I now need to specify the winding about this hole and about this hole. And once you try to do this, let's try to draw a figure. Okay, so let's see if I can do this in real time. So let's see, say if I have a base point like this. Okay, so if I choose something like this, okay, so let's call that curve F. Okay.
Hello.
Yes.
My question is exactly this: if we draw this type of curve,
yeah.
you draw here, then
yes.
Starting from I, if we draw this curve around one direction and then the in other direction,
yeah.
but anti-clockwise.
Yeah, I'll show you even something simple. I'll show you that two curves which are drawn in the same direction cannot be deformed into each other. Okay.
Yeah, so, I'm saying that the same direction cannot be. Then we have to keep the base point intact, right?
Right. Let me just go through this, okay? And maybe you can ask your question again. So if I think about another curve, which is this, okay? Right? So you would find that, so let's call this G, okay? So you would find that these two curves, okay, even though they have the same winding number, okay, so both of them to be z. So if I call this first winding number the hole 1 and hole 2, okay, so or hole A and hole B, okay, so both of them have winding 0, 1. So okay, so then you would find that this is not true, that I can continuously deform F to G. Okay, so that's because this kind of group is a non-abelian group. Okay, and one has to be careful about defining the order of composition. Okay, so one way of seeing that would be to think about a loop which looks like going about the same base point and covering this. Okay, so let's call that loop GH. Okay, so you would find that let's see if I can do this. So H inverse, okay, composed with F composed with H. Okay, I think that is okay. So by that I would mean that by H inverse I'll start here, I'll go like this. Okay, I'll perform a surgery here, I'll go like this. Okay, and then I go back in this direction. Okay, so this curve you would be able to deform into A. But if you do it the other way around, H F H inverse, okay, it is not equivalent to G. Okay, so because of this non-abelian structure, okay, one has to be careful. This notation that we introduced, okay, one has to carefully define the meaning of the notation, and just as you know, to incorporate this non-commutativity of the composition. Okay, so this is what one has to deal with, and properties of non-abelian groups would then need to be brought forward to try and characterize these things. And one can use ideas of continuous groups, locally Lie groups, to try and understand the kind of generators of this non-abelian group, etc., etc. Okay, but that's what one needs to do to try and think about how to distinguish between two loops with the same winding number vector. Okay.
Hello.
Yes.
So this is exactly my question. That in this case, we can see that the 0, 1, there is the winding number in both cases are same, but they describe the different homotopy classes. So so is it right to define by only the winding numbers?
No. So so the complete characterization of the group does not happen only through this vector. Okay, I need to specify more things to define to completely characterize the equivalence classes. Okay. More questions? Okay, Tunir.
Yeah. Okay, so we saw that the winding number does not entirely specify which group element we're talking about, but it seemed like F and G were connected by a conjugacy, a similarity transformation. So it looked like they belong to some conjugacy class. So is this is some recurring theme where winding number sort of refers to a conjugacy class, even in other manifolds?
So it depends upon it's not really conjugacy class, I think, is because it depends upon the, so I can think about H inverse, also some kind of some kind of H tilde, okay? And I need to be careful about trying to define such things. I am not sure that this relation completely defines a conjugacy class. Okay, I have to think about that.
Okay. Okay.
Yeah. Okay. More questions? Okay, good. So let's start with whatever we want to do today, which is basically focus on the XY model. Okay. So what we discovered last time, yesterday, is that because of this classification of the loops in real space and their mapping to the order parameter space, we can get topological defects. Okay, so in particular, what we want to do is to try and understand the physics of topological defects in the order parameter space, or in the order parameter field, with this famous example of XY model. Okay, so that's what we want to do. Okay. So then, just to recap, the order parameter is two-component vector, which we would almost completely focus on this representation. And we saw that the order parameter space is a circle, as we expect. Okay, and then we would focus on the first homotopy group, pi1 of S1, which is Z, which is a group of integers, and that's the other homotopy groups are sort of trivial, and we would not think about them for this. Okay, so let's try to think about what this is. This is a classification of all closed loops in the base manifold, okay, and their image given by phi of R in the order parameter manifold. Okay, so that's characterized by an integer because that's winding about a circle. Okay, good. And the fact that only in RD the loops are simply contractible, they can be continuously deformed to a point, but that then one would expect that this mapping to be trivial. But the fact that this mapping turns out to be non-trivial means that this order parameter, the mapping, has singularities. It's not continuous. So there is some problems with the mapping. Okay, at discrete points in two-dimensional space. So let's focus on two spatial dimensions. Okay, and these are the points where we have the topological defects, which in this case are vortices. Okay, good. So let's try to understand what these statements mean that we learned yesterday in context of this. Okay, so let's draw various configurations, which I guess you may be familiar with, but let's go through them in slight detail. Okay, so what does that mean? Okay, so consider two systems. So let's draw a lattice, mostly as a guide to our eye, and also to remind ourselves that there is a UV regulator. Okay, so I draw a square lattice. This is in D equal to 2, and then we draw two configurations. Okay, so these spins lie on the same plane. It is a two-component spins. Okay, and there is a configuration A, and then there is a configuration B. Okay, and this red loop is a directed loop in the base manifold. Okay, so that's the configuration A, and I have drawn a configuration B. Okay, so if I think about calculating the difference, theta is some angle. I can define a direction. I mean, it doesn't matter which direction I define, as long as I define a direction globally. Okay, I can think about this as an angle. Okay, and then if I think about trying to understand how the angles change as I go around the loop, okay, in configuration 1, okay, I'll add the difference of the angles till I go around the loop in this particular direction and add them up, okay. And this is given by this object grad theta of dr. So it's a continuous version of adding up delta theta along the loop, okay. And this, you see that this does not change for configuration A, okay. So that means that if I think about in terms of the order parameter space, okay, so this closed loop in the order parameter space, which is a theta space, okay, stays put. As I change my point, say this is 0.1, theta is this value, okay, this is the order parameter space. Okay, this is this value. Okay, if I change it, then at 2, then it still stays here. 3 stays here, and I go around the loop, it stays here. So the image of this closed loop is just this point for configuration 1. Okay. Whereas if I take this configuration B, okay, if I do this, okay, and I try to draw the same thing in the order parameter space, I have 1, 2, 3, 4. You see that as I go around, okay, as I go around, I go around this order parameter space too, and I come back, such that this integral is 2 pi. Okay. So it is in that sense the abstract things that we learned yesterday, okay, translates into non-trivial configurations of the spins, okay, in terms of in the system, okay. So then the statement about all the mathematical things that we have learned is that there is this belongs to a classification of loops which is continuously deformable to a point, but this is not continuously deformable to a point, okay. And that's because this has a singularity, okay. So think if I had completely erased the lattice and thought about only the continuous limit, okay. So then the configuration B would look like this, okay. The configuration B would look like this, okay. And indeed, at a coarse grained scale, it looks like that. So you would immediately ask, okay, what is the value of theta at this point, okay. And the answer is that it's singular, okay. Just like the singularity of point charge in electrostatics or Coulomb's law, this is also singular, okay. But now we know that this is not the self-consistent question, because if I look very closely, the singularity does not correspond to anything physical, because there is a UV regulator, and I should not really seriously think about this singularity as anything physical. But the consequences, just like the consequences of a point charge is physical, the consequences of this singularity, as we shall see, are physical. Okay. So then we can generally obtain configurations, okay, which are where the winding about a point is 2n pi, and that's the meaning of the mathematical statement that pi1 of S1 is Z. Okay. And different configurations, this is the kind of things that we were just discussing in the beginning. These are the kind of things that we expect that different configurations with the same winding number, say for n equal to 0, this is one configuration where everything is in the order parameter space in this direction, and here everything is in this direction. okay, and I can continuously deform them into each other by local spin rotations, okay, and so in that sense they are equivalent because they belong to the same homotopy class of configurations, okay. Similarly, for n equal to 1 sector, I can draw two configurations. In both these cases, delta grad theta dr, okay, is going to be 1, okay, and one is this configuration and the other is this configuration. One has been sort of obtained by rotating the other. In both the cases, the order parameter just goes around the circle, okay, as I go along this red loop. Okay. Both of them are n equal to 1, so sorry, 2 pi, okay, units of 2 pi. Okay. And then again, they can be deformed continuously into each other. Okay, so they form a class of spin configurations. Okay, so then you see that all the order parameter configurations, as far as their the homotopy is concerned, they can be classified into a countable number of sets, countable number of classes. Okay, and these are called the equivalence. These are the equivalence classes labeled by the integer, the winding number. Okay, good. So as long okay, but two configurations with different n, with n being the winding number, it's variously called winding number, vorticity, or vortex charge. Okay, they cannot be deformed continuously. Okay, so one way to see that is that suppose I take n equal to 1 configuration like this. Okay, and how do I want to how do I deform it to an n equal to 0 configuration? Okay, so I'll tell you, just like to solve the monopole problem, we took a gauge regarding the choice of the vector potential. Here we also take a gauge not in a very different sense, which so the gauge is like saying one prescription, okay, one definite prescription, but there are equivalent, many different equivalent prescriptions, and you can try each of them, and you would end up with the same conclusion, okay, about the physics. Okay, so how do I deform this n equal to 1 to n equal to 0 configuration? Okay, so one prescription is that start with the point near the singularity, okay, and then make a cut all the way to boundary. And remember, this is an infinite system. This is, we are in the thermodynamic limit, okay, and we make a cut like this. Okay, so what we have to do is to rotate all the spins on one side of the cut by in one direction, say by the amount pi roughly, because there is a 2 pi winding as I go around, and in the other direction by minus pi. Okay, and then I can do local deformations to make it n equal to 0. Okay, but then you see that I have to do this finite amount of rotation, okay, for all the spins along this line, infinite. I have to go to each spin and rotate it by pi. I have to go to each spin and rotate it by pi, and you know that the probability of these kind of things happening at in a system with large number of degrees of freedom, okay, is close to 0. Okay, so this is why in the thermodynamic limit I cannot the probability of this happening is 0. Okay, of course I'm thinking about classical systems. You can ask me questions about okay, what happens here what I have expressed is going to each spin and doing this locally. Okay, but we know quantum mechanics has this issue called tunneling, where the entire thing can tunnel. So of course its probability can be very small, but okay. So again, one can do various calculations and I haven't touched any of these things. The right place to think about, the right place to look about is a book by Rajaraman called Solitons and Instantons. And there you can find what is this tunneling probability of these kind of things, and it also goes to 0 as you take a thermodynamic limit. Okay, so so this is why the topological defects, if they are created, okay, are stable. So this is the stability that is generated at the thermodynamic limit. Okay, and these, as you can now see, have a resemblance with the kind of things that we discussed in terms of magnetic monopoles, and these are actually examples of topological quantum numbers. Okay, so remember that these topological quantum numbers have this intricate, the present class of topological quantum numbers have this intricate connection with symmetries. Okay, so there is an interplay of the what is known in modern parlance, the interplay between topological quantum numbers and symmetries. Okay, and this is a very rich structure which a large class of people are trying to understand. But I mean, let's not go there. But what I want to convey is that there is this stability, which is why if I somehow generate this n equal to 1 configuration, okay, it cannot go away from the system. It cannot decay into a n equal to 0 configuration easily. Okay, and this is why, even though it might cost energy, okay, as we will find that they cost energy, they might remain stable or have a lifetime which is quite large. Okay, so this is an example, a concrete example of the topological defect that we want to study. Okay, okay. Questions at this point? Yeah, Tunit.
Yeah, can you hear me now?
Yes.
Yes. So I'm a bit confused about that that procedure of getting n equals to 0 from n equals 1.
Yes.
Yes. So n equals 0 means that once we go around the loop about the sectors, our change in theta should be 0.
Yes.
Yes. How does this second how does this rotation with pi above and minus pi with below do that? I don't quite see it.
So so see that this n equal to 1 configuration, this kind of n equal to 1 configuration, is homotopic to this kind of configuration. And then this. Okay, so all the windings have been squeezed to this small angle. Do you understand this? Is this diagram okay?
Yeah, no, I did not understand. So what happened?
So all these windings, okay. So let's take this. Okay, I can perform a local surgery. Okay, so do you so the statement is that these two are continuously deformable because these two have the same winding number.
I see.
Okay.
Yes, to see this clearly, we'll have to go to the order parameter space, right?
Yes, yes, you have to go to the order parameter space. But if I take a loop around this, okay, I wind once, okay. If I take a loop around this space, I also wind once, okay. So I stay here for a long time, starting from here to here, okay, and then I quickly rotate about this.
Right. So all the winding is happening within this sector.
In this very thin wedge. Okay.
Right. Okay.
Okay. So now you see that this wedge extends all the way up to infinity.
Yes.
Okay. So if I have to convert it into n equal to 1 configuration, n equal to 0 configuration, I have to get rid of this wedge.
Yes.
Okay. So to get rid of this wedge, okay, I have to take all the spins in this wedge, okay, and rotate them by finite amount, okay. And one prescription is what I pointed out, and rotate them by finite amount, okay, to get to n equal to 0 configuration. Okay,
oh,
so I have to go to each spin inside this wedge, and remember we are working with n of the order of 10 to the power 23, which for all practical purposes is infinity. So the number of spins here is a fraction, finite fraction of them, right? So then I have to go to each spin and rotate them by a finite amount, okay? And the probability of happening that happening coherently at a statistical mechanics system is 0. Okay, you can try and calculate that using a Boltzmann weight of something like this. Okay, and try to see what is the probability of what is the relative probability of configuration 1 and configuration 2. Okay, and try to understand how to go how to go from configuration 1 to configuration 2, and you would see that the probability for changing finite fraction of the spins by a finite angle is 0. Okay, so that's the statement.
I see. So the idea is that there will never be a spontaneous transition within winding numbers.
Exactly, in the thermodynamic limit.
Right.
Okay. With quantum mechanics, these are classical arguments because these are classical. With quantum mechanics, we have to be more careful, but because there are these tunneling events, right? So it turns out that those does not affect, in this particular case, those does not affect our arguments. Okay, but so in the form that we are discussing is valid for classical systems. For quantum systems, we have to be more careful.
I see. All right. Yeah. Thanks.
Okay. More questions? Good. Okay. So let's try to understand this in even further detail. And now we are going towards this idea that we want to calculate, we want to understand the meaning of these topological defects. Now we have seen that they exist in case of XY model. Okay, we can work with other things too, but we in this particular context, we want to see explicitly what they do. Okay. So let's first start with how to calculate this winding number. Okay. And the way to calculate this winding number is start with the Landau Ginzburg action. Okay. You use this parametrization. Okay. And roughly at low temperature, okay, you would see that the effective action looks like this. You can put this and find out. Okay. That's the relevant part of the action. And then you try to extremize this, and that's the Euler-Lagrange equation, and that's the Euler-Lagrange equation for this action. Okay, and you want to find a solution of this with these periodic boundary conditions and the fact that you have a UV regulator. Okay, so you can try to do that. You would immediately see that you would land up with Bessel functions of the first kind and integrals of the Bessel functions. Okay, and you should try to do that. But the result that you get is something like this. Okay, this is one class of results. Okay, there is one has to look for the generalized solution. Remember, this is a partial differential equation, and you're looking for a generalized solution on a multiply connected space. So one has to look for generalized solutions in the space. Okay, and then one can find out that about this. Okay, and you would find that generalization. Okay, generically, this is proportionality, but this is equality. Okay, at at distance large compared to the core of the vortex, you would get a solution like this. Okay, and such that if you now integrate, you would get this. So you can perform these kind of things like this is a generalized the mean field theory in presence of the multiply connected surfaces, but multiply connected plane. But this is a standard technique that one can do using for a partial differential equation. Okay, so that's the way to try and calculate winding numbers. Okay, so given given a configuration, okay, one can calculate the winding number using this, and to ask for all the possible configurations, one would try to solve the Euler-Lagrange equation as we discussed. Okay, good. So that's okay. Now we know how to calculate the vortex. So this is the vortex strength. Okay. And the zero strength vortex is just long wavelength fluctuations, and we can try to understand them too. But let's ask the question, now that we understand this point defects in 2 dimensions, the vortices, what are the, how do they control the physics of the system? Okay, and in equilibrium stat-mech, we know that one of the things that we need to understand is the free energy contribution for anything. Okay, so if something needs to be relevant to the physics of the system or the properties of the system, it better have a free energy contribution. Okay, and then from the free energy we can try to take various derivatives to find out how they affect the properties of the system. Okay, so then what one wants to understand is what is the free energy contribution of these vortices. Okay, and the free energy has 2 different contributions. One is the energy, and the other is temperature into the entropy. Okay, and then what we want to understand is what is the energy contribution. Okay, and here what we haven't discussed is what is the microscopic Hamiltonian that we started out with. Okay, we'll write down a microscopic Hamiltonian in a moment, but we want a microscopic Hamiltonian which basically tries to minimize the change in theta. Remember, we are dealing with a ferromagnet. Okay, so it wants to minimize the variation in theta, and the kind of Hamiltonian that we will see actually at long wavelengths boils down to this kind of things. So this is the energy cost, and it is some grad theta square. So any grad theta is energetically costly. Okay, and then with the form of grad theta that we have, we can do this integral, and we would get something which is like this. Okay, this is the integral. So I have used grad theta, which is n by r. Okay, so that immediately says that the lowest energy cost, so n occurs in n square. Okay, because it's grad theta square, and it means that the lowest energy cost, of course, the n equal to 0, there is no cost because there are no vortices, but we are interested in contribution from the vortices, and the lowest energy contribution are from n equal to 1 vortices. Okay. So that's the contribution to E. Okay. Now, what is the contribution to S? Okay. So to ask the contribution to S, okay, we have to ask what is the how many ways can I put a vortex? Okay. So in an area which is L by L, okay, and roughly each grid space is A, okay, the number of ways I can put the vortex is L by A square, okay, at each of these places, okay. And then what? Then the log of that is entropy. So that's this object. So if I use this is see, this is a very rough estimation. I don't even want to know things exactly. Okay, I want to. Okay, these are the kind of arguments that I think you're familiar with. Okay, so then the free energy, if I put them, both the entropy and the energy goes logarithmically. Okay, and I get this. So that means that if I am at temperature, so this is the temperature. So if I am at temperature, low temperature enough such that this is positive, then the energy term dominates, and I don't want to have vortices. Whereas if temperature is large, the entropy dominates. This is nothing to do with the vortices. This is a general feature of statistical mechanics systems. Okay, and I want to maximize entropy, and I want to have vortices all over. Okay, so the critical temperature is given by this. Okay, G. So G, remember, is a spin coupling constant of the spins. Okay, some energy cost. So then we know that if I take this system, as I increase temperature, okay, below this Tc, okay, G pi by 2, okay, we would not have vortices. And if I am in temperature larger than Tc, I would have vortices. Okay. So at least we have been able to identify regimes where we have vortices and we don't have vortices, and temperature is something that we can tune. Okay, we can heat up the system, we can cool the system. So now you see that something abstract, which were part of the homotopy group, we have been able to beat it down to be able to controllably probe them. Okay, so if I want to understand vortices, I would hit the system above PC. If I want to get rid of vortices, I would cool it down below TC. And then I would measure the properties of the system above TC and below TC and try to contrast them, that how do they change. And then I can make a conclusion as to how the vortex affect those physical properties. Okay, so this is the thing that I want to do. Okay. So let's try to do exactly that. Okay, so let's try to calculate the spin-spin correlator, okay, of this particular kind. Okay, so it is basically phi 1 plus I phi 2 at R into phi 1 plus I phi 2 at R equal to 0. So that's the correlator that I want to calculate. Okay. And I want to put some H. Good. So what is the Hamiltonian? So far we have not written any Hamiltonian. We have just argued that this is what we would expect. But we now need to write down a Hamiltonian very carefully, because we want to do actual calculations. Okay, so far we have been sort of waving our hands and talking about things which really did not depend upon microscopics very well, except for the symmetries and some small things. Okay. So we want a Hamiltonian, but now since we have to be careful in writing the Hamiltonian because we are dealing with vortices, so we have to be careful that the Hamiltonian is well defined even at UV length scales, okay, or the lattice length scales, and hence we have to have a Hamiltonian which explicitly incorporates the UV length scale. And this is like putting a regulator, okay, and then in certain cases I can put the regulator to. So you see that we have been making groundwork for all these physics in our lectures, that we now have to define a Hamiltonian which specifically incorporates this lattice length and the symmetries, such that we can carefully capture the vortices. Okay. So the way to capture the lattice regulator, UV regulator, is just write down a lattice Hamiltonian. Okay, instead of writing down a continuum Hamiltonian, just write down a lattice Hamiltonian. Okay, and the other thing that we must be careful about is that the fact that the order parameter lives on a circle S1. Okay, so this theta that we have been defining is defined in modular in this range 0 to 2 pi. Okay, and we have to be careful in taking the continuum limit, keeping the UV regulator, keeping the symmetries, etc., careful. Okay, and the kind of Hamiltonian that we get, physically short-range Hamiltonian, that gives that is in conformity with this, is this kind of Hamiltonian. Okay, and you see that this I could have written as phi r, phi I, phi j. Okay, but that's an exercise you can do. Okay. And with j equal to plus 0, the ground state of this Hamiltonian is clearly the ferromagnet. Okay. So now I'm going to use some of the things that you're all familiar with. Is that at low temperature, when there are no vortices, I can expand this cosine. Okay. And I'll go back to the Hamiltonian that we have discussed, okay, in the continuum limit. And this is okay to use when there are no vortices. Okay, so this is below TC. Okay. And if I use this to calculate the 2-point correlator, I'll find that this goes as 1 over r to the power eta, where eta is this factor. Okay, such that at the critical point, if I sort of push this calculation to the critical point, the eta that I get is a number 1/4. Okay. So you see that I mean, we have been doing sort of very approximate calculations, but already we have got two things which are very which are quantized in the sense that it cannot be changed. Okay. One is, of course, the winding number, which is topologically forbidden to change, and now this particular value, it is not quantized, but this particular value of this exponent, okay, at the critical point, which is a pure number, okay, in the sense it does not have any dimension. So I can go to my the experiment or my computer, simulate this, and try to see whether the predictions are correct or not. Okay. So these are the kind of things that are a sort of universal physics. Okay, so it does not depend too much on the details. Of course, it depends upon the details. It depends upon the fact that you have the symmetry, you have short-range interactions, etc., etc. But it does not depend upon which particular lattice you are dealing with. For example, okay, you can apply this to a class of lattice. Okay, it does not depend upon what is the value of j, whether you have only nearest neighbor interaction or you have next nearest neighbor interaction, and so on and so forth. Okay, and I don't want to go into too much details, but of this. But the upshot is that you get a power law in this physically observable correlator. Okay, so that's the below TC. Okay? And remember, this is something that we can observe. Okay, so but I have to make sure that we are not violating any physical principle, in the sense that the expectation value of the spins, okay, this phi of r is still 0. Okay, and this is in accordance with Monmin-Wagner type of theorems, which says that there is no symmetry breaking if there is no breaking of continuous symmetry in two spatial dimensions at any finite temperature for short-range interacting systems. Okay, so I assume that you're all familiar with this. If not, look up. Okay, it just happens that you cannot. The mean field theory is all wrong. Okay, the mean field theory would suggest that there is a order parameter, but it's all wrong in two dimension for these kind of systems. Okay, so you see that this is very weird. Okay, I have a 2-point correlator which is power law. Okay, those who has, I mean, I'm sure that you have taken the critical theory courses, and if you have not seen this, power laws are related to critical points. Okay, here I am thinking about a continuous. So if I draw a temperature axis, okay, there is Tc. Okay, this is for this whole entire region. Okay, so this does not break the symmetry in the sense that I do not develop an expectation value of this order parameter. Okay, this is still 0, both here and here. Okay. So there is no long range off diagonal order that's developing. Yet the 2-point correlators are power law. Okay. And why am I fussing about this? And as you know that at high temperature, for example, at larger than Tc, if I do this calculation in, say, at large Tc, t going to infinity, okay, in this case, t into j going to infinity, okay, beta into j goes to 0, okay. So using this parameter, I can expand this the Hamiltonian. Now I need the lattice Hamiltonian because I have these vortices, and the vortex needs regulation, okay, and at the U level. And if I do a high temperature expansion, which is really expanding this in beta j, which goes to 0, okay, you would find that I can calculate this, okay, and it would go as an exponential, okay, with the correlation length being t over log of t over j, 1 over log of t over j. And this is something that we are more familiar with. If spins are completely decorrelated, then I expect that the correlation to fall off exponential. Okay. So you see that at high temperatures, it cannot sustain power law correlation. So as I crank up temperature Tc, okay, below this we have power law correlation, and above this we have exponential correlation, okay, with the finite correlation length. Okay. So here the correlation length has gone to infinity. So you see, even though this e to the power I theta is still 0 in both these cases. Okay. So this, you see, is very weird. Okay. I have a power law phase which looks like an extended critical point. Okay. And this is what I'm faced with. And the whole reason, as we will now see in the last half an hour or so, is because of the vortices. Okay. And okay, we won't be able to do the RG, but we will formulate this in terms of in a language that which makes the vortices explicit. Okay. So as we find that there is no vortices here, and then there are vortices here. Okay. So you see that after all the song and dance over the last week or so, we have been able to pin down a physical observable, which this correlator, which distinguishes whether this object, this topological, exotic topological objects that we have used, tried to use some abstract mathematics about, etc., make a difference to a physical observable. Okay, which we can check on our computer or in a lab where we have this kind of material. Okay, Good. So, okay. So what I, so is that okay? So right. So this is basically what I wanted to do, and what I wanted to say, and then I want to try and make some of these claims more concrete, in the sense of try to show you how to build up a concrete field theory using vortices in the next half an hour or so. Okay. So, but before we do that, I think let's pause and have questions. Okay. So, sorry, there was a question by Subhro Ghosh. The question is, I'm not quite sure, but connecting two equivalent n equal to 1 seem to me that there is a global rotation by pi/2 rather than a local rotation. Yeah, so the particular two things that I have drawn, I think that you are correct. Let's see, let's go back to this. Yeah, so the particular things that you, that's because of my limitation with drawing. Okay, generally I have taken this picture, which I could draw with a lot of difficulty, and then the easiest thing for me to do is to just take each of these spins and rotate them by pi/2. That's because of, purely because of my limitation with drawing. Okay, that in general you have to do a local deformation. So there is a well-defined local map to deform between two n equal to 1 configurations. Okay, but for the picture, yes, you're correct. Okay, more questions. So there is a question by Orko that there are many small vortices. Okay, is there a macroscopic vortex possible here? Okay, so so I don't know what it means to say small vortices or macroscopic vortices, but the vortices are non-local objects. Okay, so it really depends upon okay, let me spend let me just discuss the next topic, and you would see this. Okay, so what is the net vorticity, and so on and so forth. Okay, yeah. More questions? Okay, good. Let's start with the actual field theory. So to so that we can do some calculations or set up some calculations to understand this. And let's start with the observation that all come. Okay. So how to think about system and many vortices? So that's the question that one is faced with. Okay. And suppose this is a system, okay? And I can think about the system in various ways, and one way to think about this is the periodic boundary condition, okay? And another way is to think is rigid boundary conditions, okay? I think for our case, since periodic boundary condition would change the topology of the base manifold to a torus, let's just keep on using the Euclidean R2, but fix the rigid boundary conditions. Okay, the results does not change. So that means that what I want to do is to fix the boundary spins. Okay, think about turning on a small magnetic field and fix the boundary spins to given configurations. Okay. So that's my boundary. That's my boundary condition. It looks artificial, but in a physical system, it's a natural boundary condition to choose. Okay. So that's because at 0 temperature, we don't expect a vortex generally. Okay? I can change this boundary condition to go to what is called a twisted boundary condition, and that also can be engineered in a superfluid system or a superconducting system using a magnetic field, but let's stay away from that. Okay. Okay, so in this case, if I had taken a path which is along the boundary of the system, then the net vorticity of this is 0. Total is equal to 0. Okay. But now, if I look at local regions, okay, I could have vorticity of say N1, N2, N3, N4, okay, which are non-zero, but they all add up to 0 winding number. Okay. So if I have such situations, okay, over regions which are L. So remember, these are regions L, where L is of this pro. Okay. Then I'll say that I have vortices in my system. Okay. And the whole point that we have been using is that at what temperature do these things show up at this length scale. Okay. And a rough estimate of that is Tc. Okay. G pi by 2. That's our best guess of this. Okay. So, and once these are present, how to think about them. Okay. And this is true. I mean, one way to see that is that I can have a vortex which is +1. So let's see. A vortex which is plus. Let me not draw this. Okay. I'll draw better one. Okay. So let's draw a vortex which is like this, which is easy to see. Okay. So then this is n equal to 1 vortex, and then let's draw n equal to -1 vortex. Okay. So -1. So around this, so if I draw a loop around this, okay, I'll get a vorticity of -1. If I draw a loop around this, I'll get a vorticity of +1. But suppose I draw a loop around this. Okay, so let's try to understand what is a vorticity. So let's see. So you see that I think my drawing is not very good, but you see that the net vorticity would sort of cancel if I go along this loop, and I would get net vorticity to be 0. Okay, so that's like the composition of the vortices with +1 and -1, and then I can have these kind of situations where locally I have vortices at length scale L, but globally I do not have vortices. Okay, so that's like having many vortices, and we expect that those to show up at this temperature scale. Okay. Okay, good. So let's try to understand this effect more carefully. And what we want to understand is what we call a Coulomb's gas description of the vortices. Okay. So let's start with the Hamiltonian and do some mathematical manipulation, which is just one way to think about things. Okay. So I can write down the Hamiltonian like this. Okay, just add a constant which does not matter. Okay, so that the partition function is now given by this. Okay, I have just added this one for reason which would make our arguments sort of easy to draw pictures and do some transformations, but that's what other than it's not very important. So then the weight of this thing is given by this object, okay, and I want to understand what this object is. Okay, so if I draw this function, okay, sorry, if I draw this function, okay, 1 minus beta within a beta from 0 to 2 pi, okay, so that's so the red line is cosine theta, okay, so then the black line is 1 minus cosine theta, so this is between 0 and 2 pi, okay. So then this object, okay, which is e to the power b into 1 minus cosine theta, okay, is given by this green, the blue thing, okay, and it is very close to so and this repeats. So if I draw from 2 pi to 4 pi, this blue thing, everything repeats, okay. So that can be captured by approximately by this function where m is an integer, okay. So I think this breaks down here and here, okay. So more mathematically, this is a Bessel transform of this object, okay. So one can do this Bessel transform and try to find out the leading order corrections, but that's the motivation, that you change the potential softly, the Hamiltonian softly, such that you don't you don't change the physics, okay. And remember, the physics that we don't want to change is the fact that theta lives in this manifold 0 to 2 pi, okay, and the fact that there is a UV regulator, okay. Okay, so those two things remain intact. I still live on a lattice, and let's look at this function 2 pi m, okay. By changing m, I can make theta to be 2 pi periodic, okay. So this is basically the approximation which goes under the name of the Villa approximation or periodic Gaussian approximation. If I had put m equal to 0, this would be like a Gaussian approximation, okay. This would be like expanding the cosine, but instead of doing that, I do it at every interval. This is why it's a periodic Gaussian approximation, okay. So let's treat this Hamiltonian within this periodic boundary periodic Gaussian approximation, and then we try to understand the fallout, okay. So for our case, so let's see. So this was the Hamiltonian, and I replace this with e to the power minus beta j by 2, okay, theta I minus theta j minus 2 pi m I j square. And this m now lives on the bond of this ij, is to be summed over for all integers, okay, such that I have this repeated, I have this figure repeated over every interval of theta from 0 to 2 pi, okay. So that's the approximate Hamiltonian. Okay. So that's this thing I have written. So now let's try to make this make some more mathematical manipulations, okay. Let's decouple this, okay. e to the power x square ax square is dy e to the power y square by 2a, okay, plus I y x. This is an standard auxiliary transformation, okay, one can make, okay, and this I have used this variable. You would soon see why I am making this. So the whole aim is to make the vortex degrees of freedom very apparent, okay. So then that's the form, okay. And now with this, I can now integrate out theta ij, theta I at every side. Theta is linear. I can integrate out theta. Okay, and you say that if I collect all the terms with theta I, the term that goes with I theta I is basically sum over j Lij. Okay. So e to the, now if I integrate over theta I get this condition that sum over j Lij equal to 0 for all I, which is really like a divergence condition on a lattice on this L. And in 2 dimension, the divergence condition on L can be satisfied as follows. Okay, so I use a new notation. I call Lij. So if I and j, I call this a variable I, and this direction j minus I as mu. Okay, so think about a square lattice. So this notation is replaced by I mu. Okay. So then I can replace, I can solve this, introduce this variable psi living on the dual lattice. Sorry, this is psi. Okay, living on the dual lattice. Okay, in such a way that it automatically solves the zero divergence condition. Okay, so this is analogous to saying that this is just nothing but saying that B is equal to curl of A. Okay, but in 2 dimension. So this was for 3 dimension. I am writing everything for 2 dimension and on a lattice. Okay, so if I do this, okay, and put it back, so you see that this L square, after some manipulation, you would see that L square becomes this. And then there is a term, I have integrated this, these two out. There is a term that was left like this, which is I Lij 2 pi into Mij. Okay, so that's this quantity. Okay, so now let's try to do a partial differential. Okay, so let's put the difference. Okay, do a partial integration, and let's put the differential acting on M. Okay, so that's this object. Okay, so let's now, so this is the form that we have derived by doing this kind of algebra. Looks at this point a bit blind, but let's now try to understand these results. Okay, in particular, let's start by trying to understand what this object is. So remember, M is defined on the bonds. So if I have this, then I have M I plus X. Okay, so this is M directed along this. Okay, so this would have come with theta I minus theta I plus X minus 2 pi M I plus X. Okay, note that the opposite term, which is M I plus X I, okay, that would come with theta I plus x minus theta I minus 2 pi mi plus x I. So the only way to reconcile these two is that mi plus x I is equal to minus mi I plus x. In other words, they are directed. So the one that is opposite to this is the minus of it. So similarly, I have mi plus x, I plus x plus y. This is mi plus x plus y, I plus y. Then this is mi plus y, I. So that's, so now let's try to understand what this is. Okay. So if I try to write this down, okay. So this, so epsilon mu nu is the antisymmetric two-dimensional Levisi beta. As you know, like just like the three-dimensional Levisi beta implements a three-dimensional curl, the two-dimensional Levisi beta implements a two-dimensional curl. Okay, is this object. And when I write it out on a lattice, which is it's this, and I'm just expanding differential operators, okay, things that we have learned in high school type of things, okay, and use the fact that mij is equal to minus mji, okay. You see that this is what I get, okay. I get exactly this. Okay, the sum of these things. So I plus x, I plus x plus y, I plus y. So mi plus this, plus this, plus this, plus this. Okay. But now let's ask, what is m? Okay. And for that, we need to go back to this expression. Okay. That theta I minus theta j minus 2 pi mij. Okay, this expression, and the fact that the it wants to minimize this expression. Okay, so then it means that if I want to set this to 0, okay, that's the minimum, okay, then the difference of this, as I go from this side to this side, so theta, some value of theta here and some value of theta here, okay, so the difference of these two is given, so grad theta between these two sides is given by 2 pi m. Okay, this is, remember, this is what we started out. Okay, so similarly for this link, and this link. So if I add those things out, okay, we have nothing but the vorticity. I have used the vortex. I should have used n. Okay, but let's just right. Okay, so that's the vorticity coming from this placket. Okay, this part denotes this position of the dual lattice. So you see that this n degree of freedom that we have been carrying around within this periodic Gaussian approximation is really connected with the vorticity. And now if I put all these things together, call this object as n of I, okay, I think I'm calling it v of I, okay, and put it back here, I get this as the action. Okay, this being in our case n now, okay, the vortex field. So you see that this is an expression in terms of the vortex degrees of freedom in the system. Okay, And now, so if just to make things, so we had an action for a magnetic particle in a magnetic field which looked like this. In m by 2, plus I a dot dx dt, d tau. So remember, this is one of the things that we calculated on the first day. And I said that this in Euclidean space, this fact that this is I, leads to sort of oscillations. And there the interpretation was because of quantum mechanics, but you see that the vortex here gives rise to destructive interferences, because the presence of a vortex is like a huge change in the number of in the phase. It's a 2 pi change, whereas the usual changes are very smooth, which is given by this quantity. So if below Tc, if T less than Tc, the vortices are absent, this part is not there, then all I have is a periodic action. And this is the origin of power law. Spin-spin correlators. Whereas if I have these vortices, I would have to be careful and try to ask what is the effect of this. And then what I'll do is that you see that this is a Gaussian, this is a quadratic action. I can integrate this out. And I'll generate an action in terms of vortices, and this is things that you need to do. D square r, so d square r prime, n of r, g of r minus r prime, n of r prime. And I integrate out this psi field because it's a quadratic field. And this action now tells us how to think about vortices in this describes a gas of vortices, and this is called the Coulomb gas, because the vortices are like charges of this object of this field. Okay, good. So this is all I wanted to say. There are of course the zillions of things that I wanted to say, but what I have tried to stay away from is saying overwhelm you with too many examples, which is fairly easy to do. But rather than that, show you two examples. One from electromagnetism to introduce all the ideas that we needed, and then there was some mathematical generalizations. Of course, I didn't generalize much, but all the things that we needed, and then use those ideas in again a concrete physical context to point out how topology affects statistical mechanics system. So that's basically where I would leave, and I hope that, I mean, it's not a very satisfactory form of teaching, but I hope that with these inputs you can go ahead and try to start thinking about these and learn more mathematical aspects and the physics applications. Like I would have loved to tell you the implications of quantum mechanics in these kind of theories, but yeah, so we have to end somewhere. I think this is a good place to end, from where you yourselves can individually pick up things. Okay? Yeah. Okay. So with that, I'll stop. and you can accept questions. Yeah. So, okay.
Okay. So thanks. So there's a question by Tunid, I think.
Yeah. Go ahead.
Yes, I would once like to see the emergence of the critical temperature, just where it came from.
Oh, I see. Okay. Yeah. So
right.
this,
How does it? Yeah.
So basically, you want to see when this changes sign, this coefficient.
I see. I see.
Okay.
Okay.
So if it is positive, then having vortex is free energetically not good. Okay. Whereas if it is negative, it is I want to sort of have all the vortices I can.
Right. Right. And the capital L over here is what?
Capital L is the system size, right?
Right. It's the IR thing.
Yeah, the IR scale.
Okay. All right. All right. Yeah,
so
sense.
remember
Thanks.
that you see that this is I have been very careful in the things that are important. I haven't put this to infinity, this to 0. Then this would be a meaningless thing to write. Okay, so one has to be careful about things that which are important within the effective field theory that one is dealing with. Yeah.
All right. Yeah, thanks.
Okay, more questions. Okay, so Tunit, do you have one more question? You said.
No, sorry. I'll lower my hand.
Okay,
Sorry.
yeah. Okay, so then let's move on to Tista's question. Is there a line singularity with this point? Yeah, of course. You see that this looks like a curl. So this thing looks like a. So this relation, okay, sorry, is very similar to this relation, okay? And I could, if I were working with 2 plus 1D or 3-dimensional systems, I could have shown you that what I get is exactly the electrodynamics. Okay, that's the crowning achievement of XY duality by Chandan and Bert Halperin and Peskin and others, that they showed that this problem is exactly the problem of electrodynamics with monopoles, okay, or charges using electromagnetic duality. Okay, so then all the things that we have learned is definitely applicable. Yeah. So the comment is that repeat my calculations in 3 dimensions. And you would see that you get a theory which is exactly Maxwell's theory with monopoles.
So Subhro, I mean, this for the XY model, you kind of mapped it to a 2-dimensional Coulomb gas.
Yeah.
And then you're saying if I take the 3-component Heisenberg in 3 dimension.
No, I'm taking saying that XY model in 3 dimension.
XY, then you get the okay.
Yeah.
But if you take XY Heisenberg in 3D, yeah. Then what does it?
Fantastic. So if I take Heisenberg in 2D and 3D and ask the questions, say in 3D, and ask the question, then if I go back to my lecture notes, you would find that pi2 of so the Heisenberg system ferromagnet lives on a S2, right? It's a vector. It's a unit vector.
Yeah.
Okay, so pi1 of S2 is 0, so it does not have loops, but pi2 of S2 is Z, so then it has point defects in 3 dimensions. Okay.
Okay.
So now you can ask that what is the theory of this? Okay, that turns out to be again a more complicated version of the theory of electromagnetism with both charges and monopoles that goes under the name of complex projective field theories.
Okay.
Okay. So, yes. So, provided we incorporate all these things, we get a whole class of theories which look like theories of electromagnetism. That's the whole point that people have been realizing, that gauge theories emerge once you start thinking about the topological defects. And the naive way to understand this is as follows, that gauge interactions are basically long-range interactions. And topological defect, think about the vortex. The vortex is a non-local object. You can go to zillions of kilometers away from the vortex, but as long as you wind around it, okay, you can still feel the effect of the vortex, okay, through this winding number. Because of this long-range nature of the vortex, gauge theories or theories of electromagnetism in one form or other keep on emerging as critical theories in this context.
Okay.
Yeah.
So in 3D, of course, there is long-range order, right? In
3D, of course, there is long-range order, but I think again, someone who really pioneered this field is Chandon. So you can ask the question that suppose I have this order, okay, and then I can think about destroying the order by proliferating these defects, the point defects, okay. So then I go into a paramagnetic phase. Now, suppose I stop proliferating these defects, okay? Can I still have the paramagnetic phase? Okay, so I put an extra energy cost to these defects, okay? Because of some microscopic interactions, still I can whether I can have the transition or what would be the nature of this transition, okay? So this is the field theory that I'm right now talking about, that if you ask the question that if I have this a long-range order and try to kill it, but without having these point defects, okay, what is the theory?
Okay.
Okay. So this is also related to the nematic, that you can start with the nematic phase and try to have two isotropic phases, one with the disclinations and one without the disclinations. These two isotropic phases and the transitions turns out to be very different.
Okay. Any other questions? No. Okay. Thanks again, Subhro, and bye everyone.
Okay. Thanks. Stay safe.